Hello, this is Paul from Hotset Tech. In this video, let's prove Theorem 5.2.1. Determine if a matrix is diagonalizable. The theorem gives us a matrix is diagonalizable equivalent to n linearly independent eigenvector. Okay, the size of A is n by n. That's a good result. Let's see how. Why? Okay, let's start from A is diagonalizable. Remember A is n by n. And we need to find the equivalent condition, which is the vector eigenvector n linearly independent eigenvector. So first, by the definition, okay, so we can find this. Exists a matrix P, invertible matrix, and the diagonal matrix D. Remember that by the definition, the inverse of P times A times P equals diagonal matrix, right? Therefore, it exists. Okay, so that's the definition. And then we just look at this equation. We manipulate it. We move this to the right side. The left multiply P, so we get another form, which is no problem, right? Because P is invertible matrix and D is diagonal, we can write a specific form. For P, we cut in column by column. And for diagonal, we just needed the diagonal entry. So I can write it in this way. Okay, so this P is a column vector. Okay, all these column vectors. And then the diagonal entry is lambda 1 to lambda n. So we just break it down. And then we use the block the matrix multiplication or partition the matrix. So we get this kind of result. And the A, we can like distribute the inside, and then the right side, we just do normal calculation. Okay, so this is just by calculation. So for example, the first column should be this row multiplied by the first. That's all 0. So we only left the lambda 1 times P1, right? So the same for all the other columns. And then we break down the matrix column by column. Of course, the corresponding columns should be equal to each other, right? So we get this kind of conclusion, equivalent to. And A times P1 equals lambda 1 times P1, and A times P2 goes on. So A times NPI equals lambda I times PI, the I is from 1 to M. You are familiar about this term, right? Okay, you are familiar what this lambda from here. I can see this is exactly eigenvalue, right? This just the eigenvalue. Now, how about the PI is eigenvector, right? The corresponding eigenvector. And now we definitely get the original matrix P break it down into column, which is eigenvector. Diagonal matrix, the diagonal entry is the corresponding eigenvalue. So is PI put together linearly independent? Yeah, it is. See, we're back to the beginning. Because P is invertible. Okay. P invertible means here, I put it here, should be linearly independent, right? Because the matrix is invertible, we have equivalent theorem as all the column space as dimension, and okay, rank and all linearly independent. We put these results and these together. So now all the PI is eigenvectors. How many eigenvectors we find? And they are linearly independent, right? So I can write. Okay, so matrix A definitely has n linearly independent eigenvector. That's the condition. Okay, that's all. Thank you.